And the session will be chaired by Nazim Fetz from India Lori of France, and Mamata Duloi from Department of Computer Science, National Institute of Technology, Durgapur, India. So I would like to request the session chairs to chair the session. Thank you. Okay.
Thank you very much. So it's my pleasure to introduce Jarkko Kari. So I was going to say needless to present Jarkko, but maybe some of you would like to know a few things, because there are probably some participants to this conference who are not familiar with Cellular Automata. So Jarkko is a professor of mathematics in the University of Turku, which is southwest of Finland. And without any doubt, Jarkko is the most important and most influential researcher in the domain of cellular automata. He has organized different conferences in Turku, which personally allowed me to visit this beautiful place. Also animated many things in the domain of research. And he has an amazingly productive activity, of course, on cellular automata, many decisive results, on the theme of reversible computation, the theme of tilings, and various other domains of discrete mathematics. And I think that in all his research, Jarkko has worked with different mathematical structures, among which groups play a central role. And today we are very pleased to hear his talk on this universal tool, which are groups. And so we are very pleased to hear you, Jarkko.
Thank you very much, Nazim. That was thank you for this really nice invitation, a nice introduction, and your kind words. So let me share my screen. Let's see if this works well. Okay, you are seeing my screen now?
Yes. Good.
So I also want to thank Sukanta and all the organizers of this conference. It has been it's really a pleasure to be talking here, and the conference has been really going well and really well organized. So I will be talking about group cellular automata. So these are cellular automata that are also group homomorphisms. I will explain, of course, in detail the definitions. But before I go to the talk, like we discussed here a couple of minutes ago, I really want to use this opportunity also to voice my full support to the Ukrainian people who are really under a huge and brutal attack right now. For the past week, this has been really worrisome development in Europe, and I don't know how it's viewed in India because it's somewhat far away, but for us this has been really a shock that there is a war in the middle of Europe. And that also explains my starting slide picture here. All right, so let's go to the topic here. So as always in cellular automata, we have a finite set of states. For example, let's say blue and red. And I will be talking about cellular automata on infinite grids. So I have a grid indexed by integers, and it can be in any dimension d. And the configuration of a cellular automaton is just a coloring of the grid by states. So you assign a state to every cell in the grid. So this is an infinite coloring. I also will need the concept of colorings of a finite parts of the grid. So a finite pattern is exactly this. So you take a finite subset of cells and then you color this subset with states. These are patterns. And in symbolic dynamics, which is a very like close field to cellular automata, or cellular automata lie in this field of symbolic dynamics, the central concept is a concept of a subshift. So a subshift is a subset of configurations. So it's a collection of configurations that is obtained by forbidding some patterns. So you have you are given a set P of patterns, and that defines a subshift where you have all those configurations that don't contain any of these forbidden patterns. Now, for general in a subshift, you may forbid an infinite number of patterns, but if you forbid just a finite number of patterns, then we talk about subshift of finite type, and this is exactly what I will be concentrating here also on. So, for example, here is an example of a finite set of forbidden patterns. So let's say I forbid these 4 local patterns, which means that you are not allowed to put 2 identical colors next to each other. You are forbidding red next to itself and blue next to itself, both in the horizontal and vertical direction. And then it's quite clear that the only configurations that remain legal after you forbid these patterns are like checkerboard configurations. So in this case, in the subshift, you only have these checkerboard configurations. All right. Now, Cellular Automaton. This is a conference on Cellular Automaton, and we have seen many talks. So I think you all know what Cellular Automaton is. So you have a transformation of configurations that is defined by a local update rule. So a function that gives you the new state of a cell based on the previous states, old states in some neighborhood around that cell. Okay. Now here, the Cellular Automaton is defined for all configurations. So it's so-called full shift. The set of all configurations is full shift. So this is a Cellular Automaton on full shift. We also sometimes restrict the Cellular Automaton to some subset of configurations. So we don't need to, we don't apply the local rule on all configurations. We only have some smaller domain, subshift X. And then you just have to make sure that when you apply the local rule, the resulting configuration doesn't contain any of the forbidden patterns, so that you stay inside the subshift. So then we say that this is a Cellular Automaton on a subshift, not on a full shift, but on a subshift. All right, so for example, let's take this one-dimensional Cellular Automaton, where I take a local rule where I say that I flip the color. I have 2 colors, blue and red, and I flip the color if my right neighbor is red. So here is, let's say, a sample configuration. And now when I apply the local rule, I will be flipping, for example, this blue here gets flipped because it has a right neighbor. It becomes red. This blue didn't flip because its right neighbor was blue. And then when I iterate this, I get these dynamics, an evolution of configurations. And this particular example is an elementary Cellular Automaton. It's the elementary CA with Wolfram number 102. Namely, if I write 0 for the blue cells and 1 for the red cells, then this rule is nothing but adding modulo 2 your right neighbor to yourself, right? And this is an example of a group Cellular Automaton, as we will see in a moment. And now here, this was on the full shift. I might restrict it. So let's say that I forbid these configurations where you have different color 3 steps to the right from a cell. So I forbid these 2 patterns, which means that I'm really restricting the Cellular Automaton to configurations that are 3 periodic. So the same color has to repeat periodically in period 3. And so the restriction of the CA to 3 periodic configurations is a Cellular Automaton on this subshift. And what we saw on the previous slide was an example of a space-time diagram. So you have a cellular automaton, and now you stack these consecutive configurations of a trajectory or orbit, one after the other, and you get a drawing which represents the evolution, and that's called a space-time diagram. And if your cellular automaton is d-dimensional, then the space-time diagram is d+1 dimensional. So now you have one more dimension, which is just a temporal dimension. So from one-dimensional cellular automata, we get two-dimensional space-time diagrams. And notice that in my case, in this talk, the space-time diagrams, the time always runs from -infinity to +infinity. So there's no like time zero where things begin. The orbit is a bi-infinite orbit in time, so that we get really a configuration in d+1 dimension, because also the temporal direction goes from -infinity to +infinity. So it's a configuration in higher dimension. And of course, now for a cellular automaton, what we can do is that we take all valid space-time diagrams of that cellular automaton. So if F is a cellular automaton, I denote by STF the space-time diagrams of F. So F is d-dimensional, then this is a d+1 dimensional, and it set of configurations, and it is a subshift. It's actually very easy to see that it is a subshift, because you just forbid locally all the incorrect state changes. Like in our example, we would forbid these 4 patterns that indicate an incorrect state change. You remember the local rule? If I have red and red, it's rule 102, I should get blue. So if I have red below, that's an incorrect situation. I should forbid it. And the same for the other combinations. And once I forbid these, all the remaining configurations, two-dimensional configurations, are precisely the space-time diagrams of my rule 102. And if I'm talking about the cellular automaton on a subshift, then in addition, I will forbid in the horizontal direction the patterns that are forbidden when I'm defining X. So anyway, I get a subshift. The set of space-time diagrams is a subshift also in that case. And what this means is that decision problems about d-dimensional cellular automata kind of reduce to decision problems concerning d+1 dimensional subshifts. So if we have methods to analyze d+1 dimensional subshifts, we can use them to analyze like the long-term evolution of d-dimensional cellular automata, because space-time diagrams exactly capture the asymptotic behavior or the long-term behavior of cellular automata. But then the bad news is that, unfortunately, questions, the higher dimensional subshifts are very, very difficult to analyze. So most questions, or pretty much any non-trivial question, is undecidable in higher dimensional subshifts. So as soon as you have at least 2 dimensions, things get difficult. So even from one-dimensional cellular automata, then you get these 2-dimensional subshifts that are hard to analyze. But now, if we impose some additional constraints on cellular automata and only try to analyze some limited types of cellular automata, then we might get some kind of subshifts that can be also analyzed, and then we get algorithms with this approach. And this is what we are exactly going to do here. We will be imposing an algebraic structure and only consider cellular automata that respect this algebraic structure. And the structure we use is a group structure. So we take the following approach, that we say that the finite state set is actually now a group. Any finite group can be used. It doesn't need to be even commutative group. So I was glad to see that yesterday there was already a talk about groups, and groups were defined. So I can skip I assume now that everybody knows what a group is. It's a set with a binary operation that is associative. All right. And so now the configurations, when your states come from a group, the set of configurations naturally becomes also a group. It's a direct product of this group G with itself infinitely many times. So basically, you just apply the group operation cell-wise. So if you have two configurations, you can multiply them with each other. You just multiply the states with all cells separately. So we have the set of configurations is now also a group. And now if you have a subshift, so you take a subset of configurations, which is defined by forbidding some patterns, we say that this is a group shift if it is also a subgroup. In other words, a product of two elements of the subshift is also inside this subshift. So you don't go outside of the subshift by these group operations. So it's a subgroup. We call it a group shift. And the cellular automaton, either on this full shift, which is a group, or more generally on any group shift, is called a group cellular automaton if it is also group homomorphism. In other words, it respects the group structure. If you take two configurations, the image of their product is the same as product of their images. So we have a group homomorphism. Okay, and now immediately you can see that if you have a group cellular automaton F, its space-time diagrams forms a group shift, D plus one-dimensional group shift. The fact that the cellular automaton respects this group operation means that if you take two space-time diagrams and you multiply them with each other, the result is again a valid space-time diagram. So from group cellular automata, the space-time diagram set is a group shift. And so this means that if you have algorithms for group shifts, then you can use those to analyze your group cellular automaton as well, because you can analyze the space-time diagrams. Okay, so going back to our example, we had the rule 102. Remember, I said that if you color the... So here we had the rule that you flip the color if the right neighbor is red. And I said that if you replace red by 1 and blue by 0, then the rule is just modulo 2 addition, actually. So this is a group cellular automaton. The state set, when you view the state set as the cyclic group with two elements, so meaning that you do additions modulo 2, then this local rule is a homomorphism, and that also implies then that the cellular automaton is a group homomorphism. If you sum up two configurations, then the image is the same as the images, sum of the images of the two configurations. So we have here an example of a group cellular automaton. This is a particular kind of group cellular automaton because here we actually have a commutative group. Z2 is a abelian group. And this kind of group cellular automata is also known as additive cellular automata. But the group cellular automata are more general because the group does not need to be commutative. And so the good news to us is that there are very good algorithms for group shifts. And these are already known for a long time. From 1989, Kitchens and Schmidt proved that, first of all, every group shift is automatically of finite type. So any group shift that can be defined by forbidding some finite patterns can be defined also by forbidding just a finite number of patterns. They are all of finite type. And a second important result that provides us with algorithms is this number 2 here, which says that periodic configurations are dense in group shifts. And here dense just means in the usual metric that we have on configurations. It means that any finite pattern P that appears in some configuration of a group shift already appears in a periodic configuration of the group shift. Okay, so any P, if you have a pattern P and you have a configuration in your group shift that contains that pattern, then you know that you also have a periodic configuration that contains that pattern. And by period, I mean here strongly period. So in 2 dimensions, it just means that you have a repetition. The same things in a configuration repeat both horizontally and vertically. And in D dimension, it just means that it's periodic in all directions. And these 2 results that I again wrote up here are powerful tools. They give us algorithms. First of all, to tell if a given pattern appears in some configuration of a given group shift. Okay, so you are given the forbidden patterns that define a group shift. So let's say this set Q here, some forbidden patterns, and you are given a new pattern P, and you want to know, is there a configuration that contains P but does not contain any of these forbidden patterns in Q? And there is an algorithm to solve this. For arbitrary subsets of finite type, this is known to be undecidable. But for group shifts, we have an algorithm based on these results by Kitchens and Schmidt. And we get an algorithm by using really a standard argumentation by Hao Wang, already in 1960. Basically, we have a semi-algorithm. We have semi-algorithms for positive cases and negative instances of the problem. For the positive instances, we get the algorithm from this property 2. So what you can do, if you want to see that P appears in some configuration of the subshift, you know that if P appears in some configuration of the subshift, it appears in some periodic configuration. So all you have to do is that you enumerate periodic configurations one by one until you find the one that contains pattern P. Okay. Of course, if P doesn't appear in any configuration, then this just keeps on going forever. But if P does appear in some configuration of the subshift, you will eventually find the periodic configuration that contains it. And then for the negative instances, we have another way of another semi-algorithm. So you know that if this works in any SFT, so we use the property 1 here. You know that if P does not appear in any configuration, you know that there is some number n such that any n by n extension of P contains a forbidden pattern. So what you do here is that you just try with bigger and bigger n until you find a big number n, so that you try all possible extensions of P into an n by n pattern, and you just verify that you always have a forbidden pattern there. All right, and now you have these 2 semi-algorithms, and you can run them in parallel, and you really get an algorithm for testing if a pattern P appears in a configuration. All right, and from that, we can design easily another algorithm to determine if 2 given group shifts are the same. So you give 2 sets of forbidden patterns that define a group shift, and you want to know, are these group shifts identical? And you can do that based on this previous algorithm. Let's say you are given sets Q and P. These are sets of forbidden patterns. And now the group shift defined by Q is a subset of the group shift defined by P if and only if none of the forbidden patterns in P appears in any configuration in XQ. If XQ does not contain any configuration with the forbidden pattern P, then you know that every configuration in XQ, because they don't contain elements of P, they are all contained in XP. So now we just have to check for each pattern in P whether it belongs to XQ or not. And that's exactly what our previous algorithm gives us. We can do that. There's an algorithm for testing that. And P is finite. You have just finite number of patterns to test. So that's really an algorithm. And now exactly the same way we can test the inclusion in the opposite direction. And together you have an algorithm for testing equality. And that will be extremely useful to us. All right, so now what our technical contribution here is, before we go to the applications on cellular automata, is the following. We also showed that you can algorithmically construct projections, lower dimensional projections of group shifts. So if you give me a group shift in any dimension, and then I can form the lower dimensional subshift or group shift that consists of these slices that appear in elements of your higher dimensional group shift. So like here is a two-dimensional configuration, and I take a projection, which means that I just take a one-dimensional slice from it, and I get this one-dimensional configuration. And so I take all the one-dimensional configurations that appear as slices in elements of the subshift. That's the projection of your subshift. And what we showed is that you can algorithmically construct this subshift. So you can find forbidden patterns that define this one-dimensional subshift if you are given as input the forbidden patterns for this two-dimensional subshift. And this works in any dimension, not just when you go from dimension 2 to dimension 1, but you can do it from any higher dimension to any lower dimension. And so notice that the projections are automatically group shifts, because when you multiply two configurations, the result is again a configuration. So if you multiply two slices, it's again a valid slice that appears in some configuration. All right, and so how do we use this technical contribution? So we apply this to space-time diagrams. So you have this group cellular automaton F, and then you know that the set of space-time diagrams is a group shift. And so we know that we can effectively form any lower dimensional projections of these space-time diagrams. And we are especially interested in two particular projections. The first one is the projection, one-dimensional projection in the temporal direction of the space-time diagram. And this is called a trace subshift. Okay, so this is in other words, you have all the pi infinite sequences of states that may appear in some cell in the orbits of this cellular automaton. So temporal sequences at the cell, possible temporal sequences at the cell is a subshift, trace subshift. And it is just a projection of space-time diagrams, one-dimensional projection in the temporal direction. And by our theorem, you can effectively construct this trace subshift. It's a group shift, and we can construct it. And the second kind of projection we are interested is in the spatial direction. And this is so-called limit set of the cellular automaton. So you take slices in the space dimensions. And now this means that you have all the configurations that appear in some orbit. In other words, configurations that have an infinite sequence of pre-images, because my space-time diagrams run, remember, the time runs from -infinity to +infinity. So a configuration appears in a space-time diagram if and only if it's a configuration with an infinite number of primitives, you know, this configuration that belongs to some bi-infinite orbit. So this limit set is again group shift, and we can construct it. Okay, and now once you build a trace subshift and you build a limit set, you can decide you can analyze the group cellular automaton. You can decide many questions about the cellular automaton. Is it injective? Is it surjective? Is it nilpotent, periodic, equicontinuous, sensitive, and so on and so on. And I will, in the rest of the talk, I will show some of these decision problems and how we can use these limit sets and trace subshifts to solve them. But first, let me remark that the concept of a group cellular automaton is a generalization of a concept of an additive cellular automaton or so-called linear cellular automaton. And these have been studied very much over the past 50 years, and many algorithms have been designed to solve exactly the kind of questions that I'm solving here. Okay, so I already mentioned it before. So additive CA is just a group cellular automaton where the group is commutative. So you have finite abelian group as your state set. And the linear cellular automaton is even more restricted. The alphabet is a finite commutative ring, and the cellular automaton is a linear function on this finite commutative ring. And so the results that we have, these decidability results, they generalize many decidability results that have been established for linear and additive CA over the years. And interestingly, I find it very nice that we kind of unify the proofs that have been designed for this additive and linear cellular automata, and the proofs have been quite different for different types of cellular automata in the past. Now we have a kind of a unified way of analyzing them. And let me also mention that these linear and additive cellular automata have turned out to be quite nice with many applications in various domains. We have seen actually quite many talks about them already in this conference, and I'm sure we will see more. So, for example, we have seen how linear cellular automata are used in pseudo-random number generation, which is very important in cryptography. It can be used in error-correcting code, circuit synthesis, VLC design, testing, and pattern generation, fractal generation, and so on. But I should point out that in many of these application domains, they concern cellular automata that are finite in the sense that you just have a finite number of cells in your array. And sometimes also they are non-uniform, so you have a different linear or additive local rule in different cells. So I emphasize that in my talk, I always have the infinite grid. So we have really an infinite number of cells, and the local rule is uniform, so the same rule everywhere. All right, so let's go first to injectivity and subjectivity. These are properties that have been studied from the very beginning of cellular automata theory. So we say that the cellular automaton is injective. It can be on a subshift, it can be on a full shift, or it can be on a subshift. We say it's injective if every configuration has at most one pre-image. So distinct configurations are mapped to distinct configurations. And it's surjective if every configuration has at least one pre-image. And here is just briefly what is known about these properties in general, or also previously in algebraic setting. So we know that there's an algorithm to test if a given one-dimensional cellular automaton is injective or surjective, even on any SFT. But if you go to 2 dimensions, the questions already become undecidable. So it's non-trivial, or it's not possible to effectively test from a given local rule of a cellular automaton, whether that cellular automaton is injective or surjective. Now, in the algebraic setting, it's known that these properties can be tested also in higher dimensions. It has been shown for linear cellular automata over any finite commutative rim, actually, by Sato in '93. But so what we are we can now show with this our technique is that it is decidable for any group CA over any group shift in any dimension, whether this cellular automaton is injective or surjective. Let's look at surjectivity first. Well, the cellular automaton is surjective if and only if the limit is the whole configuration space. Because surjectivity means that every configuration has a preimage, which means that every configuration belongs to a bi-infinite orbit. Every configuration appears in a space-time diagram, so it's in the limit set. And so the decidability now follows immediately, because we know that we can effectively form this limit set. It's a group shift also. And we are given this X as input. The domain of our cellular automaton is a group shift. And now we have an algorithm for testing whether these two group shifts are the same. Remember, we had an algorithm for testing equivalence of equality of two group shifts. So that's it. We can decide surjectivity. Now, injectivity, almost as easy. Of course, for a group homomorphism, which the group cellular automaton is, we know that injectivity means is equivalent for the kernel of being a singleton set. So the kernel of a homomorphism is just a set of configurations that are mapped to the identity element. So in the group, we always have an identity element, and we look at the preimages of the identity element, and this should be a singleton set, and that's enough to test injectivity of the map. Now the kernel is again a group shift, because if two configurations are both in the kernel, then their product is also in the kernel. And we can construct it effectively because you just forbid all the neighborhood patterns of the cellular automaton that are mapped by the local rule into a non-unit element of the group. They are forbidden, because then you are not in the kernel if you have such a pattern in your configuration. And then you forbid, of course, all the patterns that are forbidden in X when you define X. So we can form the kernel. It's a group shift. And now we just have to test whether these two group shifts are the same. And again, that can be tested since they are group shifts. So injectivity can be tested in this manner. Okay, I have some time, so I have some properties that I was thinking whether to have time to present them or not. So I think I have time. So let me talk a little bit about the property of surjectivity of a subshift. So we say that the subshift is a surjunctive subshift if every injective cellular automaton on that subshift is surjectivity. So if injectivity implies surjectivity, then we have a surjunctive subshift. And that seems to be the case for many, many subshifts. So full shifts, for example, are well known to be surjunctive. It's a classical result that every injective cellular automaton on a full shift is also surjective. Injectivity implies surjectivity. This follows, for example, from the well-known Garden of Eden theorem immediately. There are wider classes of SFTs where we know that they are surjunctive. Fiorenci has proved it for strongly reducible SFTs, so you don't need to worry about the term if you don't know it. Just mention it if somebody knows this term. And we know that not every SFT is surjunctive. I mean, there are examples of one-dimensional SFTs where injectivity does not imply surjectivity. But for group shifts, they are automatically always surjunctive. In fact, this holds for any subshift where the periodic configurations are dense. Always subject. The injectivity implies subjectivity. Maybe I will skip this. Maybe I will skip this proof to save some time. Another property related to injectivity and subjectivity, somehow, or actually to subjectivity, is the question about periodic points, temporally periodic points, and their denseness. So we say that the configuration is temporally periodic if you come back to that configuration after some time when you iterate the cellular automaton. So it's a periodic point in the dynamical system. So you return it back to the configuration after some time t. And we say that the configuration is jointly periodic if it is periodic both in the temporal direction and in the spatial directions. Okay, so you have like this horizontal and vertical periods and also temporal periods, let's say in the two-dimensional case. Said to have a dense jointly periodic points if, well, these jointly periodic points are dense. Okay, so but it means that if any pattern that appears in some configuration of your subshift appears also in some jointly periodic configuration, in some configuration which is periodic in temporal and spatial directions. And this is probably one of the best known and longest-standing one of the longest-standing open questions about cellular automata is whether every surjective cellular automaton on a full shift has dense jointly periodic points. Is it true that every finite pattern appears in some periodic point in surjective CAs? And this has been studied a lot in the past. So this is known to be case under some dynamical properties like closingness or equicontinuity in one dimensions. And also for group cellular automata in one dimension, this has been established in 99. And same year 99, this was also shown for this additive CA in any dimension D. But now actually from this results by Schmidt and Kitchens that we talked about before, it follows that every surjective group CA certainly has dense jointly periodic points. Maybe briefly, I can explain why. So here, take any finite pattern that appears some configuration of your subshift. So I have like indicated here in yellow. You have a finite pattern that appears in some element of your subshift. And now our cellular automaton was assumed to be surjective. So it means that this configuration where this pattern appears belongs to some space-time diagram. So your pattern belongs to some spatial slice of a space-time diagram. Okay. And now by the results by Kitchens and Schmidt, we know that in group shifts, so this set of space-time diagrams is a group shift, and we know that in the group shifts, any pattern that appears in a configuration appears in a periodic element. So it means that there is a periodic space-time diagram that contains our pattern, this yellow pattern. So there is a periodic space-time diagram, but of course the periodic space-time diagram just means that the slices that you have are exactly jointly periodic. They are temporally periodic because you have period in the temporal direction, and they are also spatially periodic. So you have this pattern appears in a jointly periodic configuration. So they are dense. All right. I mentioned earlier these properties, nilpotency, periodicity, and so on. So very easily we can also show that all these questions are decidable for group shifts. Let me recall these concepts quickly. So we say that the cellular automaton is nilpotent if in the limits that you only have one configuration, only a single configuration there. In other words, no matter what configuration you start with your cellular automaton, it eventually goes into that single fixed point configuration, which is common to all configurations. Okay, and we say that the cellular automaton is periodic if there's a period p such that when you iterate the CAP times, you always get back to the same configuration. So there's like all configurations are periodic with that same period p. And we say the cellular automaton is eventually periodic if after a finite time, it becomes periodic. So there may be some transient time n when something different happens, but after that time n, you start repeating with period p in the dynamics. And all these questions are to decide if a given one-dimensional cellular automaton has any of these properties, these are all known to be undecidable. There's no algorithm to tell if a given cellular automaton is nilpotent or periodic or eventually periodic for general cellular automata. But now if you go to group cellular automata, all these questions can be decided, and not only in one dimension, but they can be decided in any dimension, and not only on full shift, but on any group shift x. All become decidable. And the proofs are now are really very easy. So nilpotency, well, nilpotency, like I told you, means that the limit set is a singleton, and in case of a group cellular automaton, that limit set has to be exactly the identity element of the group, because that's a fixed point automatically. The identity element is automatically a fixed point of a homomorphism. And now we know that we can construct a limit set. And this is another group shift that we have available, and we just test if they are the same. And equality can be tested. So that's the algorithm for nilpotency. Eventual periodicity, it actually means that the trace subshift is finite. So on the traces in the temporal direction, you have some transient time, which don't show up in the space-time diagrams because my space-time diagrams run from -infinity to +infinity. And so there you have just a period in the space-time diagram, temporal period, which means that the trace subshift is finite. Okay, but now we know that we can construct the trace subshift. It is a one-dimensional group shift. And it's very easy to test whether a given one-dimensional SFT subshift of finite type is finite or not. Yeah. So finite can be tested, and therefore eventual periodicity. And then periodicity, well, a cellular automaton is period if it is eventually periodic, and it has to be injective because the transient time has to be 0. Which means exactly that it's injective. So periodicity means just testing these two properties, and we already have algorithms for both of them. We have an algorithm for injectivity, and we have algorithm for eventual periodicity. So we have algorithm for periodicity as well. Very quickly, I want to mention also some dynamical properties. So as dynamical systems, we have properties like related to sensitivity to initial conditions and so-called mixing properties. And I will discuss these a little bit. So a cellular automaton is equicontinuous at the configuration if its dynamic is stable at that configuration, in the sense that small changes in the configuration do not affect the dynamics much, so they don't propagate. Okay. I'm not giving a formal definition here. And for cellular automata, for general cellular automata, then you have basically three possibilities. You have the possibility that every configuration is an equicontinuity point, which means that your dynamics is stable everywhere. At the opposite extreme, you have sensitive cellular automata. They are sensitive to initial conditions where you don't have any equicontinuity points, basically, or you don't have stability anywhere. So every configuration can be modified very little so that that change propagates and becomes big when you iterate the cellular automaton. It's like the butterfly effect. Small change in the initial configuration propagates and becomes big in time. And then for general cellular automata, you have also the third possibility, which is that some configurations are equicontinuity points and some are not, which is a kind of between these. But for group cellular automata, it turns out that you actually you don't have this middle option. You just have two possibilities. So you have a dichotomy. Either every point is an equicontinuity point, or none of them are equicontinuity points and the system is sensitive. The middle ground is missing in group cellular automata. And whether your cellular automaton, group cellular automaton, is equicontinuous or sensitive, so it would be interesting to test which of these two properties your cellular automaton has. That can be done. There's an algorithm for that. Namely, turns out that this equicontinuity is exactly equivalent to being eventually periodic. And we already know that eventual periodicity can be tested. There's an algorithm for it. So we can test equicontinuity also, and sensitivity, because it's just a complement of equicontinuity in this case. So these are decidable. Mixing properties are a kind of another family of properties that people study in dynamical systems. This just means that do you have orbits that come close to all configurations, dense orbits, and things like that, or can you get from any part of the phase space into any other part of the phase space? Does it mix in time? I just give results here. I absolutely have no time to give all these formal definitions. So I just mentioned that in a group CA, we know that transitivity is equivalent to mixingness. Transitivity is a kind of mixing property that in general is weaker for dynamical systems, at least. And but here we were not able to design this mixingness property or transitivity, which is equivalent. So we only have a semi-algorithm for non-transitivity or non-mixingness, but we were not able to get the semi-algorithm for the other direction. So that kind of remains an interesting question to look into. So I think I will stop here so that we have a couple of minutes for questions if somebody wants to ask something. So in conclusion, all the results that we mentioned very heavily relied on these seminal results by Kitchens and Schmidt from '89, these two results about group shifts. And based on these, we were able to design algorithms for many, many questions concerning group cellular automata. And like I mentioned, I like this way of proving these decidability results because they really unify many of the results and generalize results that have been proved before in various different means. And like I mentioned, maybe as open problems, well, I didn't mention this, but now I mention it. We didn't find any undecidable properties so far. So every question that we looked at turned out to be decidable. So would there be some natural questions about group cellular automata that cannot be algorithmically decided, or maybe would it be possible to prove some general theorem stating that everything in some suitable logic language of logic would be decidable in the case of group shifts? I don't know. And then as a specific open question, yeah, I mentioned that this transitivity, we were not able to prove it to be decidable, only semi-decidable. And that's an interesting question. Most likely it is decidable, but who knows? Like I said, it seems very difficult to be able to implement any like Turing machine computations in group cellular automata, which would be a kind of necessary to get some undecidability results. So it seems that questions are decidable in general. So I stop here, and I thank you, and I'm open for questions.
So thank you very much. Thank you very much, Jarkko, for this fascinating talk. So let us take the question of the audience now.
Actually, I wanted to ask some question. Hello, sir. This is Supriti.
Hello, Supriti.
Yes, how are you, sir?
I'm good. How are you? Good to hear
fine,
you.
Sir. Thank you, sir. It's a long time I have been talking to you. Sir, actually, I wanted to know that we can decide which one is group CA or not, right? But is it the case for non-uniform CA also? Can we decide whether a non-uniform CA is group CA or not?
On a full shift, certainly yes, because at least on a full shift, you just have to test the local rule and see that the local rule is a group. Every local rule has to be a group homomorphism.
If each of the rules, each of the rules is a group homomorphism, then we can say that this CA is a group CA.
Then it is a group CA, exactly.
Okay.
Because it means that the product of any two configurations is mapped into the product of the images, separate images of the two configurations, because it happens locally in every cell. So yes, it's equivalent.
Thank you, sir.
Thank you.
Good. Are there other questions? No question? Let me see if I see someone raising his or her hand. Yes, Kamalika? I see a raised hand. Okay. Yeah. Sorry, Kamalika, but personally I cannot hear you.
Can you hear me?
Now I hear you, yes.
Okay. So yeah, sir, I was asking whether if the CA is not additive or linear, in that case, what will happen? Can we get some kind of decidable properties for the other reversible CAs?
So if it's not additive or linear, it can be still group CA, because like I said, the group CA is more general. The group can be non-commutative. And so then we have all these algorithms, because all my results were for general group CA. And it actually might be very interesting to see, because this additive and linear CA have so many different applications, but I haven't seen that many for cases where the underlying group would be non-commutative group. It might be interesting to see if they can be used also for some, I don't know, pseudo-random generation or whatever. But then when you go beyond the group CA, in general case, all the questions that I talked about are basically undecidable. In some limited cases, in limited setups, they might be decidable. Like in many of the slides I mentioned, in which setups they might be decidable, like injectivity and subjectivity are decidable for one dimension, but not in higher dimensions, and so on.
Sir, I was thinking while watching your talk that you are taking slices of space-time diagram. So if some of your theories could be applicable for irreversible CAs, say for 1D only, for ECA only, then can I get some idea about what can be the evolution of from the space-time diagrams, what can be the evolution after some time steps without calculating or without evolving the CA?
Yeah, so in general, it wouldn't work out because the space-time diagrams are no more group CA, and then also the slices are not group shifts, and they are not anymore subsets of finite type. Like for arbitrary general cellular automaton, this limit set, which is the horizontal slice, subsets of finite type, and we cannot construct it effectively anymore. So that's why things get undecidable there. But maybe it would be interesting to find some intermediate cases. So like restrict to some cases where we know that the limit set is of finite type, and then maybe some of the methods would work also.
Okay, thank you, sir.
Hello, sir.
Hello.
It's Schmidt, sir. I have a
Hello,
question, sir. Actually, sir, my question is the theorem which are applied for the group CA. Is it applied for non-uniform CA, or can we apply it in non-uniform CA?
That's a good question. So things get very difficult when you have an infinite grid, and then it's non-uniform. So somehow to have like good questions to ask even means that somehow maybe the local rules, how do they repeat like periodically, so that the different local rules, you cannot just have like them arbitrarily assigned to the infinite number of cells, because then just the description of the cellular automaton is not finite. But let's say if the rules repeat periodically, then it actually works as a group CA. You just have to take this period as let's say meta cell or meta cell, and then you actually have a group CA. So in that case, the non-uniform case it kind of reduces to this uniform case. But then you have other kinds of non-uniform cases, like let's say you have a finite number of cells where you use a different rule and then some other rule in the on the infinite background. Then I don't know. Maybe some of the methods might work also in that case. I would guess. I would get it. Yes.
Thank you.
Good. Is there a last short question?
Yeah, may I ask? Imagine?
Yes.
Thank you, Jarkko, for this excellent talk. I have one query. As you were saying that for the group CA, the periodicity, whether it's periodic or not, that is decidable, right?
That is decidable. Yes.
Decidable. Okay. So if I want to decide the length of, the length of period, after how much time the initial configuration will return back, is it possible?
Right. Yes, you can do that. So you first test that your cellular automaton is periodic, and then you can try the periods like just one by one, 1, 2, 3, and you can form this nth iterate of your cellular automaton, and you can test is it an identity map or not. But it's of course extremely inefficient. That's another thing that I didn't mention in my talk, that I was only worried about whether it's decidable or undecidable, but the algorithms that come up are extremely inefficient. So I would not recommend anyone to try to implement these in practice. I mean, they are totally horrendous in terms of practical applicability, more like a theoretical interest, whether they can be decided in theory. But yeah, so we can find out that period, definitely.
Does it mean that period is always finite?
It's always finite, yes. That's the definition in the periodicity, is that you have a finite number so that you come back always in that time.
Okay, thank you.
So,
are there other questions? Maybe to finish, Jarkko, you can tell us how you feel about what you did, in the sense that I recently read a text from the mathematician Henri Poincaré, who was saying that the goal of mathematics was to get a new language to unify things that are at first sight different.
right.
So is it the approach you are working on, and what you achieved? Is it like the dream of the mathematician to get more and more unity in a field with diverse results?
Well, yeah, that's exactly what I try to emphasize in my talk, that we were unifying these different methods of doing these proofs and unifying the concept of additive CA and other kinds of groups into linear CA into a kind of a way how to deal with all of them with the same tool and same tools. So in that sense, I think, yeah, unifying these different approaches was a goal here. Yeah.
Good. Thank you very much, Jarkko.
Thank you,
And